The first time I heard about graph theory, my initial assumption was that it might be related to things like graphs of functions, as those were the only types of graphs I was familiar with at that point. But the relatively new mathematical field of graph theory turns out to be in fact something totally different. What exactly is a graph? A graph G is defined by a pair of a finite set V of nodes, also called vertices, and a set of edges E. The edges of a graph represent relationships between the nodes. In most cases, the nodes are labeled with numbers or alphabetical letters to distinguish them from each other. For the graph above, the set of nodes V is V equal to the set containing the elements 1, 2, 3, 4, and 5, and the set of edges E is defined by the following sets. The graph G is then the pair of V and E. Regarding this edge set, the graph consists of edges connecting the nodes 1 and 2, 1 and 3, 1 and 4, 2 and 3, 3 and 4, 3 and 5, and 4 and 5. A graph like this is called an undirected, unweighted graph. Before we proceed, a quick remark about the notation used in this course. An edge connecting two nodes U and V in an undirected, unweighted graph will be denoted as UV or SVU. Both notations have the exact same meaning. An incredible amount of problems in the real world can be modeled through a graph, especially when the instances of the problem stay in some relationship to each other, like in a network. Let's say an edge in this network between two individuals represents a friendship between them. By the selection of any person from this network, we can explore all of their friends by tracing where the edges connected to them led. More formally, the friends of the person in the yellow node, let's call this node U, define the neighborhood of the node U. In a general graph, the neighborhood N of U consists of all nodes V in the set V that are reachable from the node U by using a single edge. So an edge connecting U and V that is included in the edge set E of the underlying graph. Every friend of the person in the yellow node is called an adjacent node of the yellow node. Or in math language, every node contained in the neighborhood set N of U is an adjacent node of U. The last definition counts the amount of edges attached to the yellow nodes. This number is called the degree of a node. In this graph, the degree of a person corresponds to the number of friends the person has. But important, the degree of a node doesn't always represent the number of neighbors of a node. This is only the case if there isn't more than one edge between two nodes. The yellow node here has obviously a degree of 5. An interesting property of graphs becomes visible when adding all degrees of all nodes in a graph together. For this, let us iterate through every node in the graph, determine its degree, and add all degrees together. This node has a degree of 6, so our total degree becomes 11. The next node has a degree of 9, so our total degree becomes 20. The next one has a degree of 8, so our total degree becomes 28, and so on. At the end we obtain the sum of the degrees of all nodes. And what property does this number have? It is even. In fact, this is not a coincidence here. Independent of the specific graph, the sum of all degrees is always even. Furthermore, knowing the sum of all degrees in a graph allows also for the calculation of the total number of edges in that graph, what might sound surprising at first. The summation of all degrees in the graph in the animation yields 3192. In fact, the graph in the animation is a complete graph, meaning a graph in which every node is connected to all other nodes excluding itself. More detailed, this graph has 57 nodes and every node is connected to 56 equal to 57 minus one other nodes. Therefore, the sum over all degrees here is equal to 57 times 56. And the total number of edges in this graph is given by half this number, because by summing up all degrees one counts every single edge twice. This lets us to suspect that the sum of all degrees in a graph is always equal to twice the number of edges in the graph. And this is in fact exactly the case. It holds the following formula. The right-hand side of this equation is equal to twice a number, which is obviously even because it's divisible by 2. Now, since there's an equality sign in the middle, the left-hand side is even as well. Furthermore, if you consider having n many nodes v1 to vn in a graph, this implies that the sum of all degrees is even. And the left-hand side can only be even under certain circumstances, for instance if all degrees are even or if exactly 2 nodes have an odd degree. But if the number of nodes with an odd degree is, for example, 1, it follows immediately that the total sum cannot be even. What I want to say is that the number of nodes with an odd degree in the graph is always even because the sum over all degrees has to add up to an even number according to the above formula. And the interesting implication now is that this holds for every graph. A corollary from this is the handshake lemma, which tells you if there is a party of people who shake hands, the number of people who shake an odd number of other people's hands is even. Observations like this that helps us to better understand the structure of graphs are very important in graph theory. And for some certain graphs there are indeed still many unsolved mysteries waiting to be solved. Very important in graph theory are so-called graph traversal algorithms, which aim to visit, to explore, or to process every node in a graph. The range of application of such algorithms is very large, and there are basically 2 commonly used different types of them. The one algorithm starts at a node and systematically visits all of its neighbors. Then it proceeds by visiting the neighbors of the nodes that have been visited first, leading to a layer-by-layer exploration of the graph. This algorithm is known as the breadth first search (BFS) algorithm. The subgraph generated by this algorithm is known as a BFS tree, which offers valuable information about the underlying graph, for instance shortest paths from the starting node to all other nodes, if the length of a path is characterized by the number of its edges. In contrast to that, the other algorithm follows the approach to explore the graph in depth first. It selects in every iteration a neighbor node, possibly a random neighbor, as the next node and continues in this way until it gets stuck. Then the natural way out, think about a maze, is to backtrack to the last node with unvisited nodes in its neighborhoods. This algorithm is known as the depth first search (DFS) algorithm. The resulting subgraph, the DFS tree, looks a bit familiar to a maze. And indeed, with the right modifications, this simple algorithm can also be used to generate a maze. As seen in the animation, the white rectangles are the nodes and the dark gray rectangles are the edges of this graph. I will put now a white rectangle behind this graph to make things easier to see. The only thing to do now to create a maze is to run the DFS algorithm on this graph. Note that through the application of DFS, this maze has a solution, since DFS calculates a path from the starting node to all nodes in the graph. In other words, there is a path from the starting node to any other node here. In a city, it is important that every village has access to electricity. The distribution of the electricity wires can be visualized using a graph. Furthermore, one can search for subgraphs in this graph such that every village in the city has exactly one access to electricity. Such subgraphs of a graph have to contain obviously every village and are called spanning trees. In the real world, each edge would be assigned a label representing the costs associated with distributing wires along the corresponding edge, which represents a street. The general goal then should be to minimize the costs for the distribution of wires such that every town gets access to electricity. Therefore, one would search for a minimum spanning tree in the given graph, which is a spanning tree with the least possible total cost. Very important in graph theory, especially in the era of navigation systems like Google Maps, are shortest path algorithms. Think about a map of a country where each node represents a city and the edges are labeled with costs such as the kilometer distances between two nodes or the duration to travel between two adjacent nodes. Now imagine that you are a pizza delivery guy tasked with delivering a pizza to a client located far away. In this scenario, choosing the shortest route with respect to the edge labels is crucial to ensure that the client doesn't have to wait too long to receive his order. These were just a few examples of graph theory problems that we will analyze throughout this course, which hopefully gave you a glimpse of a feeling of what graph theory problems are about. In fact, we've seen that graph theory is a very strong and broad field in mathematics with various practical applications. But despite its current significance, this field is relatively new. To understand the origin of graph theory, we have to go back in time to 1736. In the center there's nobody else than Leonhard Euler, who probably doesn't need any further introduction due to his significant contributions to some of the most famous mathematical formulas. Euler lived nearly in the same time span as the two outstanding mathematicians Gottfried Leibniz and Isaac Newton. These three mathematicians are probably among the most famous and influential mathematicians to have ever lived on this planet. In the time around the year 1735, the citizens of a Prussian city named Königsberg, which was not far from St. Petersburg, the home of Leonhard Euler, used to spend Sunday afternoons walking around their beautiful city. While walking, the citizens decided to create a game for themselves, their goal being to devise a way which they could walk around the city, crossing each of the 7 bridges in Königsberg exactly once. Even though none of the citizens of Königsberg could create a route that would allow them to cross each of the 7 bridges exactly once, the question whether this is even possible remained unanswered. But luckily for them, it didn't last long before Leonhard Euler was confronted with this question. Euler worked on complicated and complex problems, so one could have assumed that he wouldn't invest time in a problem seemingly so unrelated to the field of mathematics. But there is a certain property about this problem that piqued Euler's curiosity. Euler's letters to other mathematicians revealed his fascination for this problem. The aspect was the problem's underlying structure, and Euler noticed that solving it didn't require specific details about the bridges or landmasses. Instead, he realized that the problem could be abstracted, leading him to set the foundation for a concept that is known today as graph theory. Furthermore, he referred to this problem as being in a field mentioned by Gottfried Leibniz called Geometria Situs, the geometry of position. A way to abstract such a problem as the 7 bridges of Königsberg problem can be illustrated using a simplified model with 4 islands and 7 bridges. Every island represents obviously a node and every bridge an edge. A walk of a citizen in Königsberg has also a name in graph theory. It is a walk in the underlying graph, translating to a sequence of adjacent nodes in the graph. While we try to walk through this graph and to cross every edge exactly once, we will always face the problem that at some point we will get stuck at the nodes, because we won't have any unused edges left to take anymore. However, this will always be necessary since we will still have other edges left that we have to visit. In fact, it doesn't even matter which walk you take here, because you will never succeed. But why? In very simple terms, this has something to do with the degrees of the nodes in this graph. Is it guaranteed in this graph that if one edge leads to a node, another edge will lead out of that node again? Very soon we will see an explanation for this. But before we start dealing with the analysis of such walks, we should give them a name. Fundamental definitions in graph theory are definitions of a path, a cycle, a trail, a circuit, an Euler trail, and an Euler circuit. Many people get confused here, therefore it is very important to consider these definitions very clear. Starting with a path is a walk in a graph such that all visited nodes in the walk are distinct. So in the general definition of a path, it is not allowed to use nodes more than once. A cycle is a path that is closed, meaning it starts and stops at the same node. Furthermore, the length of a cycle is given by the number of used edges in the cycle. A trail is a walk such that all used edges are distinct. Furthermore, it can visit nodes more than once. A circuit, not to confuse with a cycle, important, is a closed trail. And now the point where many people get confused. An Euler trail is a trail that visits each edge in the corresponding graph exactly once. While such a trail is often referred to as an Euler path, it basically isn't a path because it can visit nodes more than once. These definitions are unfortunately not always consistent. If you hear people talking about an Euler path, it's very likely that they mean an Euler trail, as the term Euler path has become established. And now the last definition, the definition of an Euler circuit. An Euler circuit is a circuit that visits each edge in the graph exactly once. What we are searching in Königsberg is either an Euler circuit or an Euler trail. What one can observe immediately is that the graph in the bottom right corner here, which contains an Euler circuit, has only nodes with an even degree. And in fact, a graph that contains at least one node with an odd degree cannot have an Euler circuit. The explanation for this is also not very deep. If you try to start your Euler circuit with a node that has an odd degree, for example a node with a degree of 3, then you will leave the node at the beginning, traverse somehow through the graph, come back to the starting node at some point, and if you leave it then once again, you won't be able to return to this node anymore as required for an Euler circuit. Otherwise, if you start your Euler circuit with a node with an even degree and encounter a node with an odd degree during your traversal, you will be forced to use all of its adjacent edges during your route, and then you will get stuck. Furthermore, Euler's results in this context can be found in literature by searching for Euler's path and circuit theorems, or just by searching for Euler's theorems. Euler showed the three following assertions. Assertion 1, a graph in which all nodes have an even degree has an Euler circuit. Assertion 2, a graph with exactly two nodes of odd degree contains an Euler trail, but not an Euler circuit. And assertion 3, a graph with any number of odd nodes other than 0 or 2 will not have any Euler trail. We've already discussed the first part of the proof for assertion 1 of this theorem. If you're interested in more, I encourage you to try to prove or to argue why the other assertions must hold. Considering the last statement and our previous graph from the 7 bridges of Königsberg problem, we can observe immediately that all nodes have an odd degree, implying that this graph has neither an Euler circuit nor an Euler trail. From 1736 to now, graph theory has undergone significant development. Various types of graphs have been born, and graph theory has found application beyond mathematics, especially in computer science. In the following, we will explore some important types of graphs and especially their roles in data structures. Basically, graphs in graph theory can be classified into 4 classes. Undirected unweighted graphs, graphs where edges have no direction and no associated weights. Directed unweighted graphs, graphs where edges have a specific direction but still no weights. Undirected weighted graphs, graphs where edges have no direction but have associated weights. And directed weighted graphs, graphs where edges have a specific direction and also have associated weights. While dealing with graph theory, one will come across many types of graphs. A very important type that we've already seen at the beginning of this video is the so-called complete graph, where every node is connected to all other possible nodes in the graph. Furthermore, this graph is complete and consists of 5 nodes, which is why this graph is often referred to as K5. This graph is also in the class of the 4-vertex connected graphs, because every node has exactly 4 neighbors. More precisely, a graph G is said to be k-vertex connected if it contains at least k plus 1 vertices, but does not contain a set of k minus 1 vertices whose removal disconnects the graph. While talking about complete graphs, there are also many other important complete graphs like k6, k7, k8, and so on. What's fascinating is that adding more nodes to a complete graph intensifies its beauty and complexity. It's captivating to see how such a simple concept can evolve into a captivating piece of mathematical art, where every new connection adds depth to the overall structure. But don't worry, there are still many other important and beautiful graphs that we will explore. Another important graph is, for example, the Euler Graph, which is a graph where every node has an even degree, ensuring the existence of an Euler circuit. Also an important kind of a graph is the Hamilton graph, which is a graph that contains a Hamiltonian cycle, a cycle that visits each node exactly once. Finding such a cycle is a challenging problem, as we will see in the next video. If you deal with graph theory, you won't be able to avoid bipartite graphs. A bipartite graph is defined as a graph whose nodes can be divided into 2 disjoint sets, in such a way that no 2 nodes within the same set are adjacent. In this graph we have a partition into red and blue nodes, and none of the red or blue nodes are connected to nodes of the same color. The only connections in this graph are between the red and the blue nodes. This is a bipartite graph without cycles. Important to note is that a graph with cycles can also be bipartite. Furthermore, a graph is in general bipartite if and only if every cycle is even. This means that every cycle in the corresponding graph has to consist an even number of edges. Of course, the concept of partitioning the nodes of a graph into such sets can be generalized. For example, consider a tripartite graph. Note that it is not necessary for a graph to be connected, meaning that not every node in a graph has to be reachable from an arbitrary node. A graph can be made up of many connected components. A forest describes a collection of trees. Trees are graphs that have always the minimum number of edges necessary for connectivity. A tree will be typically illustrated with a structure like this. Specifically, this here is a binary tree. Visualized in this way, a binary tree can be divided into layers. On each layer or depth there are nodes, and the number of layers -1 represents the height of the binary tree. The crucial characteristic of a binary tree is that each node has at most 2 children. In addition, each node belongs to a specific class of nodes. The top node of a binary tree, known as the root node, has no parent node. A node in the tree that has at least 1 child is called an inner node. A half-leaf is a node that has only 1 child, And a leaf node is a node that has no children. Another important type of a tree that is similar to the binary tree is the ternary tree, in which each node can have at most 3 children. But let us focus here on binary trees. Binary trees are used in various applications, for instance to visualize the execution of many recursive algorithms. Here for example the execution of a recursive function that calculates the 8th Fibonacci number. The famous sorting algorithm quicksort selects a pivot element in every iteration. Then it rearranges the array such that all elements to the left of the pivot element are smaller and all elements to the right of the pivot element are larger than the pivot element. This process continues recursively on the left and right subarrays. The entire process can be visualized with a recursion tree. In most cases, one will be interested in the height of this binary tree, as it provides information about the algorithm's execution time. In general, there are many types of binary trees with different names over which I will give you a small overview. To mention here is for instance the complete binary tree. This tree is characterized by the property that it must be completely filled on every layer of the graph, except for the bottom layer, and all nodes must be as far left as possible. If we add a new node to this graph, it has to be inserted as a left child of the node 5. But adding a new node as for example a left child of the node 8 or as a right child of the node 5 would violate the property of the tree to be complete, as it needs to be filled layer by layer from left to right. Another important type of a binary tree is the so-called full binary tree. In a full binary tree, every node has either 0 or 2 children, but never just one child. But if a binary tree has only one child per parent, either a left or a right child, and this through the entire tree, then it is called a degenerated binary tree. Another important type is the so-called perfect binary tree, characterized by the property that every layer is completely filled with all leaf nodes on the same layer. A general goal is to ensure that binary trees are balanced, meaning that each node's 2 subtrees have heights that differ by at most 1. But more about this later. Maybe you are asking yourself why binary trees are so important. To understand this, we have to consider a few basic data structures, starting with the array. An array is a simple data structure that stores a collection of elements, each element identified by an index. Very important for us, especially in the context of the graph traversal algorithm DFS, is the so-called stack. A stack is a data structure that follows the philosophy that elements are added and removed from the top of the stack. The 2 main operations for a stack are the push operation, which adds a new element to the top of the stack, and the pop operation, which removes the most recently added element from the stack. This principle is known as the last in first out LIFO principle, which is similar to stacking coins. Another important data structure that we will see in the context of the BFS algorithm is the queue. A queue is a data structure that follows the principle of adding elements to one end and removing them from the other. The 2 main operations for a queue are the enqueue operation, which adds a new element to the back of the queue, and the dequeue operation, which removes the oldest element from the front. This ensures that the elements are processed in the order they were added, following the first in, first out FIFO principle, similar to cars waiting in a line in front of a traffic light. As mentioned before, we will see both data structures in action in the video about graph traversal algorithms. A very frequently used data structure is the linked list, or rather the so-called doubly linked list. A doubly linked list enables immediate access to the first and last element via the head and tail pointer. Each element, so each cell, consists of a so-called key value, here the number stored in the rectangles, and also a pointer to the previous element in the list and another one to the next element in the list. Binary trees come now into play when it comes to the time complexity of basic operations such as inserting, deleting, and searching for elements in the list. Time complexity refers to a measure of the amount of arithmetic operations an algorithm takes to run as a function of the input size. It helps to understand how the algorithm's performance scales with increasing input size. Here the so-called Big O notation has become established. In very simple terms, O of 1 refers to a runtime that is at most constant, O of log n to a runtime that is at most logarithmic, O of n to a runtime that is at most linear, O of n squared to a runtime that is at most quadratic, and so on. For those of you who want to be very precise, there exists also a formal definition that clearly indicates whether a function belongs to a specific class like O of n. Additionally, there are even other notations. However, understanding these concepts is unnecessary at this moment. If you want me to cover them in a separate video, please write it in the comments. In a doubly linked list, inserting at the end requires constant time, while deleting and searching operations require linear time. And the explanation for this is also very straightforward. To insert an element at the end of a doubly linked list, we simply need to adjust the corresponding pointers. When searching for an element, we may need to traverse through the entire list, where we have to check whether each element is the one being searched for, resulting in linear time complexity in the input size. And to delete a specific element in a doubly linked list, we first need to locate the element, which requires searching through the entire list in the worst case and results therefore in linear time complexity. After locating the element, deletion involves only adjusting of pointers, a task that can be completed in constant time. Therefore, the overall time complexity for deletion is linear, dominated by the search process. The issue here lies obviously in the linear time complexity for both deleting and searching operations, what naturally leads to the immediate question, can we do better? The answer is yes, and the first step toward constructing such a data structure with a better delete and search time complexity is the binary search tree. Note that when considering tree data structures, the numbers in the nodes represent the key of the elements stored in those nodes, and not the labels of the nodes themselves like before. A binary search tree is a binary tree with the additional property that the key of a parent node is always larger than the key of its left child and smaller or equal to the key of its right child. In this case, 17 is smaller than 23 and is therefore a left child of the node 23. 34 is larger than 23 and is therefore a right child of the node 23. This property holds for all nodes in the tree. Furthermore, we can imply when considering the root node that every node in the right subtree must have a key value larger than or equal to 23, and every node in the left subtree must have a key value smaller than that. Now, the time complexity for the three basic operations depends obviously linearly on the height of the tree. Why that? Well, let us consider some examples. Let's say we want to insert a node with a key value of 8. Where do we have to insert it to not violate the binary search tree property? Well, 8 is smaller than the key value of the root node, which is 23. Therefore, we know already that this element has to be placed somewhere in the left subtree. 8 is also smaller than 17, so that we can imply that 8 has to be placed somewhere in the left subtree of the node with the key value 17. Finally, 8 is also smaller than 9, so that the element will be inserted as a left child node of the node with the key element 9. Now once again with a node with a key element of 29. 29 is larger than 23, smaller than 34, and larger than 27, what implies that we have to insert this node as a right child node of the node with the key element 27. So in both shown cases we had to process a node on every layer, which is why the time complexity of the insertion depends linearly on the height of the tree. Also for the search operation we have to traverse in the worst case as many nodes as there are layers in the tree. When searching, for example, for the node with the key element 29, we have to check first whether 29 is smaller, larger, or equal to 23. Since 29 is larger than 23, we have to check in the right subtree whether 29 is smaller, larger, or equal to 34. Since 29 is smaller than 34, we have to explore the left subtree attached to the node with the key element 34. And since 29 is larger than 27, we have to go to the right subtree of 27, where we finally find the node with the key element 29. The deletion of a node is a bit more complicated and depends obviously on the node that should be deleted. To delete a leaf, it's clear that we can simply remove it from the tree without any further adjustments. In the case that we want to delete an inner node or even the root node, we have to replace the corresponding node with an appropriate node such that the binary search tree property won't be violated. This is also possible in O of H. So in comparison to the doubly linked lists, the time complexity for the insert operation in a binary search tree may have worsened, while the time complexities for deleting and searching have potentially improved. This improvement is potential because these two operations in the binary search tree can have the same time complexity as in a doubly linked list. Because a significant problem with binary search trees is that they can become degenerated, and then the height h of the tree coincides with the number of elements in the tree. So where is our progress? Progress is achieved when we can guarantee that the height of the tree is bounded by a term that is smaller than n, so smaller than the number of elements in the tree. And for this reason people invented binary search trees with additional properties like the red-black tree. A red-black tree guarantees a height that is smaller or equal to 2 times the logarithm to the base of 2 of n plus 1, where n denotes the number of nodes in the tree. Such a tree satisfies the following properties. Property 1, every node is either red or black. Property 2, the root node is black. Property 3, if a node is red, its children must be black. I call this one the not red rule. And property 4, for each node any path from this node to a leaf or half-leaf has the same number of black nodes. We will not analyze such a tree or the corresponding insertion and deletion processes in detail here. But I think it's not difficult to see that inserting or deleting nodes in this tree can easily lead to a violation of the red-black tree property, which is in general not easy to restore. Including the assertion that the height of such a tree is never larger than the mentioned logarithmic term, it can be concluded that the time complexity for all 3 basic operations is always logarithmic. Note that we have improved the time complexity for deleting and searching from linear in a doubly linked list to logarithmic in a red-black tree. But this improvement has also its price, because we have no longer constant time complexity for insertion in a red-black tree. Close related to red-black trees are AVL trees. AVL trees are binary search trees where the heights of the 2 child subtrees of any parent nodes differ by at most 1. The small indices over the nodes in an AVL tree represent the balance factor indicating the height difference between the left and right subtree of each node. This balancing prevents the tree from a degeneration to maintain efficient search, insert and delete operations. Therefore, the time complexities for the 3 basic operations in an AVL tree coincide with those for the red-black tree. In summary, we can say that binary search trees are important data structures that are particularly useful for search processes. The last type of trees that we will discuss in this video are heaps. Basically, there are 2 kinds of heaps: max heaps and min heaps. A max heap is a binary tree, but not a binary search tree, important, with the property that each node's key is greater than or equal to the key of its children. Analogously, a min heap is a binary tree where each node's key is less than or equal to the keys of its children. We can observe in the animation that 9 is larger than 8 and 5, 8 is larger than 7 and 2, 5 is larger than 3 and 1, and 7 is larger than 4 and 6. Furthermore, we can observe that the node with the maximal key in the whole tree is always the root node. Heaps have many applications in practice, for instance in Heap Sort, a popular sorting algorithm. The algorithm begins by constructing a complete binary tree from the elements in the array, filling the tree from left to right until all elements have been inserted. The resulting complete binary tree is obviously not a heap, but it is very easy to transform it into a heap, or here specifically into a max heap. The transformation can be achieved with a helper function, which I call here buildMaxHeap, and which uses the so-called heapify algorithm. Once the max heap is constructed, the root element can be swapped with the last element in the array. At this point, the last element in the array is in its correct position and can be removed from the heap. Since the heap property is violated due to the last swap, we must transform the tree back into a max heap. And this is possible with the heapify procedure. This may sound complicated, but the only thing that really happens here is that the root node will be swapped recursively with its larger child node. And that's basically the key idea of Heap Sort. Reconstruct the heap, swap the last element with the root element, reconstruct the heap again, and so on. This process continues until all elements are properly sorted. In the last segment of this video, we will explore efficient ways of representing graphs on a computer. Of course, a graph cannot be passed to a computer in its visual form. It must be described in a more abstract way, using numbers or letters. And the first obvious and also naive approach in doing so is by defining the graph over a finite set of nodes V and a set of edges E according to its definition. Unfortunately, this approach is very inefficient. Just consider the task of finding all neighbors of the node labeled with 18 in this graph. You'd need to search through the entire set of edges for all edges containing the number 18, resulting in a time-consuming operation, especially for large graphs. But don't worry, there are more efficient ways to represent a graph. To mention here is, for example, the representation of a graph through an adjacency matrix. This matrix is a square matrix where the rows and columns correspond to the nodes in the graph. The existence of an edge between two nodes will be indicated by a 1 in the corresponding cell of the matrix, while a non-existence of an edge between two nodes will be denoted by the number 0. The node 1 is connected to the nodes 2, 3, 5 and 6. Therefore we insert the number 1 into the second, third, fifth and sixth column in the first row of the adjacency matrix. Similarly, node 2 is connected to the nodes 1 and 6, what implies that we insert the number 1 into the first and sixth column in the second row of the adjacency matrix. Analogously for the other rows. Another way of representing a graph, maybe the most popular one, is through an adjacency list. An adjacency list represents a graph as an array of lists, where each list contains the nodes adjacent to a particular node. This representation is often more memory efficient than the adjacency matrix. Remember here that even if a matrix contains only zeros, these zeros have to be stored on your computer. So if you choose to use an adjacency matrix anyway, it can be more efficient to use sparse matrices, because sparse matrices store only the non-zero entries of a matrix, significantly reducing the memory usage, especially for graphs with few edges. So these were two approaches to represent an undirected, unweighted graph in a more efficient way. Of course, these approaches work also for a directed, unweighted graph. Nevertheless, it is important to observe that for an undirected, unweighted graph, the adjacency matrix is always symmetric, which may not be the case for a directed, unweighted graph. Maybe you're asking yourself now, what is with weighted edges? Well, weighted edges aren't a problem either. In an adjacency matrix, the weight of an edge between two nodes will be inserted into the corresponding cell of the matrix. In contrast to that, in an adjacency list, the weight of an edge can be stored along with an adjacent node. This can be accomplished by representing each element in a list as an object or tuple containing the adjacent node and the weight of the corresponding edge. With this being said, we've reached now the end of this video. Thank you for watching and don't forget to subscribe for more videos.